If your matrix dimensions in a large language model are off by even like a single value, a billion parameter architecture just crashes instantly.
Oh, yeah, completely flatlines.
Right. So, welcome to the deep dive. If you're listening to this right now, chances are it's pretty late.
Usually is for this stuff.
Yeah, maybe you have your IDE open, the dark mode is glowing, there's a lukewarm cup of coffee on the desk, and you're just trying to make sense of a code base that feels, honestly, a little bit like magic.
I think we've all been there.
Exactly. You read the research papers on AI, and they're filled with these beautiful, intimidating Greek letters, right? And summation symbols.
Oh, the math is gorgeous on paper.
It is. But at the end of the day, a compiler doesn't understand Greek letters.
No, it definitely doesn't.
A processor
Yeah.
doesn't understand theory. It understands arrays. It understands memory allocation. It understands actual code.
Yeah, exactly. The hardware just wants the numbers.
Right. So our mission for this deep dive is simple. We are taking the mysterious, highly theoretical math of LLM attention mechanisms, and we're translating it into the actual matrix shapes and the code logic that software engineers work with every single day.
It's the ultimate translation job, really. Because there is this massive gap between reading an elegant equation on a PDF and, actually writing the multidimensional array operations that bring the AI to life.
It's a huge leap.
It is. I mean, the math is spotless in theory, sure, but the code is where the rubber actually meets the road.
Oh, absolutely.
You get that dreaded dimension mismatch error, or your GPU throws an out-of-memory exception, and your whole late-night coding session just grinds to a complete halt.
The absolute worst feeling.
Right. So breaking this down mechanically, like step by step, is really the only way to understand what's actually happening under the hood.
Yeah, and any good software engineer knows you can't write the logic if you don't understand the shape of your data.
Rule number one.
It's exactly rule number one. So we have to start at the absolute beginning of the attention mechanism, which is the input.
Right. Before any of the magic actually happens.
Yeah, before the magic. We have our input data, which the source material refers to as matrix X.
Matrix X, yeah.
And its shape is strictly defined as N by D model.
Right.
So N D model.
Right.
Let's visualize this for a second, because we know N represents the sequence length and D model is the embedding dimension.
Yeah, the depth.
But for someone used to writing like standard object-oriented code, looking at a 2D matrix of floats to represent human language is, well, it's a bit of a leap.
It's a massive conceptual leap, but sequence processing inherently demands it.
Why is that?
Well, think about why a two-dimensional array is mechanically necessary here. You need one dimension representing time or, sequence order.
And that's our N.
Exactly. That's your N. If you feed the model a sentence with 1,000 tokens, N is exactly 1,000.
Makes sense.
But then you need another dimension representing the depth of representation for each specific moment in time.
Yes.
And that's your D model. Because if you tried to flatten this out into just a single 1D array.
Oh, that would be a mess.
Total mess. You would completely lose the boundaries between the tokens. The model would have no structural way to know where one word ended and the next one actually began.
I sometimes picture it like a train sitting on a track.
Oh, I like that.
Yeah, so the N dimension is the number of train cars. You have a sequence of cars lined up one right after another.
Right. Sequence order.
Exactly.
Yeah.
But a train car can't just be an empty shell. It has to carry actual information.
Yes, and inside each of those cars is a massive cargo manifest.
The cargo manifest.
That manifest is the D model dimension. So it's not just a single string containing a word, right? It's an array of, say, 4096 floating point numbers.
Wow, just for one word.
Just for one token. And those numbers are detailing every conceivable property of that specific token.
Like what kind of properties?
Like, is it a verb? Is it plural? Does it carry a positive sentiment? Or, is it part of a coding language? Or is it a French poem?
Right.
All of that semantic and syntactic meaning is encoded as numerical values spread across those 4096 floats.
That's crazy to think about.
It is. So you basically have a sequence of N cars, and each one is carrying a D model-sized array of data.
Okay, so setting the stage with this exact N D model shape allows the architecture to process the sequence systematically.
Exactly.
We have our N train cars sitting on the track. They're loaded up with their highly detailed manifest. But right now, they're just sitting there in isolation.
Totally isolated.
Right. Car number 3 doesn't know anything about car number 7.
Nothing at all.
But if we're building an AI that actually understands language, We need to calculate how much these individual cars care about each other.
Yes, we need to force them to interact.
Force them to interact, because human language is entirely driven by context, right?
100%. I mean, a word in isolation means almost nothing. Its definition is basically sculpted by the words surrounding it.
Right.
So to compute how much each token should attend to every other token, the code executes this massive matrix multiplication
Okay, between what?
between two new representations that are derived from those train cars.
Okay,
You have Q, which stands for query, and K, which stands for key.
right. Query and key. I always try to map these concepts to something human,
Yeah. Analogies help a lot here.
It feels a bit like a massive professional networking event to me.
Oh, that's a great way to look at it.
Yeah. Imagine every single token walks into this huge convention hall. Q, the query matrix, is essentially the name tag that says, hello, I'm looking for an expert in Python.
Right, searching.
Exactly. It represents what the token is searching for so it can understand its own context better.
Yeah,
And then K, the key matrix, is the other name tag the token wears.
the offering.
Right. The one that says, hello, I offer expertise in Python. It represents what the token possesses that might be useful to others in the sequence.
That networking analogy captures the intent perfectly, because multiplying Q and K is mathematically equivalent to every single token walking around that room.
Scanning name tags.
Exactly, scanning everyone else's name tags and calculating a numerical compatibility score.
But as engineers, we have to look really closely at the mechanics of that interaction in the code base, right?
We do, yeah.
Because we don't just multiply Q by K, we multiply Q by the transpose of K.
The transpose.
And that transpose isn't just a mathematical flourish.
No, not at all.
It's a strict structural requirement to
Yeah.
actually make the code compile.
Right, because if Q is shape and D model and K is also shape and D model, you literally can't multiply them natively.
Right, the matrix math just fails.
Yeah, the inner dimensions don't match up for matrix multiplication. You just get a massive error thrown right in your console.
Because matrix multiplication requires the number of columns in the first matrix to equal the number of rows in the second matrix.
Exactly. So what do? We take K and we transpose it.
We flip it.
We literally flip it on its side in memory. So it transforms from N D model to D model N.
Okay, so the dimensions swap.
Right. And now, when we multiply Q by this transposed K, we're multiplying a matrix of shape, N D model, by a matrix of shape, D model N.
And those inner D model dimensions,
They cancel out. They completely cancel out in the operation.
leaving us with a resulting matrix shape of N. Yeah.
Yes. And that NN matrix is the absolute core of the attention mechanism.
Dog cord of everything.
Yeah. By flipping K on its side, the math basically forces a complete cross-referencing loop.
Like a grid.
Like a perfect grid. It mathematically ensures that every single token's Q, it's what I'm looking for, vector, is compared against every single other token's K, their what I offer vector.
So you end up with this perfect N by N grid.
Exactly. If you look at, say, row 3, column 7 of that matrix, the specific floating point value sitting right there tells you exactly how much token 3 needs to pay attention to token 7.
That's incredible. So we essentially built this massive compatibility matrix for the entire sentence.
We did.
We have our Q and K matrices, we executed the transpose, we ran the matrix multiplication, and now we're staring at this beautiful N grid of relationships.
It's elegant.
It sounds totally flawless. Yet, when engineers actually run this exact code, especially as their models get larger, right? Like when they increase the D model size,
Oh, yeah. They hit a wall.
they run into a complete brick wall. There's a hidden mathematical trap that occurs as those dimensions grow.
And it is a nasty trap, too. It can completely silent fail your model if you aren't actively looking for it in the logs.
Oh, wow.
The source material highlights this explicitly, actually. It says, when you take the dot product of two random vectors of dimension D, the expected value of the result scales with D.
Wait, hold on. I'm losing you there. I want to make sure the developers listening truly understand what's happening under the hood here.
Tara, let's break it down.
If I take two completely random vectors, just arrays filled with like random positive and negative floating point numbers, and I take their dot product, shouldn't the positive and negative numbers just sort of cancel each other out?
Right. Like, why would the final result scale up and blow out my values just because the vector itself is longer?
That is a very intuitive assumption. And honestly, it's exactly why this bug catches so many developers completely off guard.
Okay, so why doesn't it just average out to 0?
Let's trace a dot product manually.
Right.
Like the way a simple for loop would actually execute it.
Okay.
What are you doing mechanically? You take the first element of array A and you multiply it by the first element of array B.
Right.
Then you do the exact same thing for the second elements.
Okay.
And the third. And then, and this is the absolutely critical part, you sum all of those individual products together into a single variable.
Ah, so you're accumulating everything into one massive summation.
Yes. You are continually adding to a running total. So if your vectors have a mean of 0, your individual products will indeed be a mix of positive and negative numbers.
Right, they fluctuate.
They do. The average of those products stays around 0. However, as you sum them up, the variance, like the raw spread of these numbers, explodes. Because you're just doing it so many times.
Exactly. Because you're summing up D-independent components, a massive D-model dimension means a massive summation loop.
Right.
If your D-model is, say, 64, your dot product results will have a certain variance.
Not too bad.
Right. But if your D-model is 4096, you are summing up 4096 individual independent products.
So the variance just goes off the charts.
Yes. The resulting values sitting inside your NN matrix are going to be astronomically larger simply because you ran the loop more times.
Okay, so if the numbers in the NN matrix get huge, what actually breaks downstream? Like, why is that a problem for the code?
Because of the very next step in the attention mechanism, which is passing those values through a softmax function.
Softmax?
Right. Softmax's job is to turn raw scores into percentages like probabilities that sum perfectly to 100%.
Got it.
But the mathematical formula for softmax involves raising e to the power of your input value.
Oh,
Exponents. So it is extremely sensitive to large numbers. If you feed it a matrix with huge blown-out integers, the exponentiation just goes completely off the charts.
it just skyrockets.
Exactly. Softmax aggressively pushes the largest value in the row to exactly 1.0, and it squashes every other value down to basically 0.0.
Oh. So it turns into this harsh winner-take-all scenario rather than like a nuanced distribution of attention?
The nuance is completely destroyed, and when that happens, your gradients vanish.
Vanishing gradients, the classic nightmare.
The worst. For the software developers listening, vanishing gradients basically mean the feedback loop that updates the model's weights hits 0.
It just stops.
Yeah, the mathematical signals telling the neural network how to improve just flatline entirely. The model effectively freezes and stops learning completely.
Wow.
This is why the expected value scaling is so dangerous. So to fix it in the code, you have to mathematically divide the raw result of your dot product by the square root of D model.
Wait, so you're manually shrinking the variance back down?
Yes.
You're forcing it back to a stable, standard, normal distribution before passing it to the softmax function.
Exactly. It acts as a built-in stabilizing mechanism. You scale the numbers down, softmax behaves gracefully, and your model continues to learn without freezing up.
That's brilliant. Okay, so we scaled our dot products. The code is running smoothly. The gradients are healthy. The arrays are updating.
Things are looking good.
Yeah, but taking a step back to look at the architecture we just built, we hit a severe logical limitation, don't we?
We do. We really do.
We're computing this beautiful NN attention grid, but we're only doing it once.
Just the one time.
And doing this entire cross-referencing process just one time is wildly insufficient for understanding complex data, right?
Yeah, what we've constructed so far is formally called single-head attention.
Single head.
Right. And the source material notes a strict bottleneck here. In single-head attention, each token only computes one single set of attention weights.
So it only gets one perspective.
Exactly. It's only allowed to form one perspective on its relationship with the rest of the sequence.
Let's relate this to a software engineer's daily workflow, because I think it helps ground it.
Sure.
Imagine you're doing a massive code review on a critical pull request, right? You're staring at 1,000 lines of code. But the strict rule of this specific review is you are only allowed to look for syntax errors.
Oh, that sounds awful.
It is. You can only look for missing semicolons, unclosed brackets, indentation issues. And that is it.
Well, you'd catch the syntax errors, sure, but you'd be completely blind to the bigger picture.
Exactly. You would miss the glaring logic bugs. You would miss the SQL injection vulnerability. You would miss the memory leaks and the horrible performance regressions because you were only looking at the code base through one extremely narrow lens.
Yeah, and to do a proper, robust code review, you need multiple reviewers, or in our case, multiple heads, scanning the exact same code for entirely different reasons.
One reviewer looks for syntax, one looks for security vulnerabilities, one looks for efficiency.
And human language requires that exact same multidimensional analysis.
How so?
Think about a single word in a paragraph. Let's take the word bank.
Okay, bake.
To truly parse that word, a token needs to attend to different things in the sequence for completely different reasons. One set of attention weights might need to scan the surrounding nouns to determine if the text is talking about a financial bank or a river bank.
Right, that's context resolution.
Exactly. But simultaneously, that very same token needs to look at the subject of the sentence to ensure grammatical agreement.
Oh, right.
Or it might need to look at an adjective 3 paragraphs back to understand the sarcastic tone of the author.
That's a lot for one token to do.
It is. And if you only have one single NN matrix, you are forcing the mathematical model to average all of those distinct critical needs grammar definition tone into one single floating point number.
Oh, so it just washes out the nuance.
Totally washes it out. It averages away all the detail.
So upgrading to multi-head attention fundamentally changes the code base then.
It does. Instead of doing one massive matrix multiplication to get one grid, we split the work up.
How does that look in memory?
Well, if our D model is 512 and we want 8 heads, we don't just multiply the memory requirements by 8.
Right, that would explode the RAM.
Yeah, instead, we slice the D model dimension into smaller chunks.
Oh, okay.
Each head gets 64 dimensions. We run the Q and K transpose multiplications multiple times in parallel.
Okay, so each head generates its own unique NN grid.
Exactly. Head 1 learns to track grammatical structure. Head 2 learns to track pronouns. Head 3 tracks tone.
It allows the architecture to build this rich, layered understanding of the relationships between the train cars.
It is an incredibly elegant solution to the bottleneck of a single perspective.
It really is. So we've built an incredible piece of software here.
We really have.
We have multiple heads running in parallel, tracking all these different linguistic nuances.
Yeah.
We perfectly scaled our dot products, dividing by the square root of D model so our softmax functions don't blow up.
Yep, gradients are stable.
We have our Q multiplied by K transpose, making sure every token interacts with every other token. It feels like we're ready to commit the code and deploy.
It does feel that way, doesn't it?
But there is a massive conundrum staring us right in the face.
The timeline problem.
We have a timeline problem. When are these tokens looking at each other?
This brings us to the actual crux of sequence generation. Because based on the exact tensor operations we've outlined so far, we have built what is formally known as bidirectional attention.
Bidirectional, okay.
Yes. Everything built up to this exact moment allows every token to attend to every other token in both directions.
Past and future.
Past and future.
Wait a second. Let me look at this from a text generation perspective.
Yes, sure.
If we're trying to build an autoregressive AI-like, a model that generates data one step at a time, predicting the next word based on what it just wrote.
Right.
And our current code, this beautiful NN matrix we just built, allows a token to look at the future tokens. Isn't that literally giving the model the answer key to the test before it takes it?
It is the literal definition of cheating.
Yeah.
You've spotted the fatal flaw for autoregressive generation. Let's walk through a really concrete example.
Okay, let's do it.
Say you're training the model on the sentence, "The cat sat on the mat."
Simple enough.
The goal of the AI at step 3 is to look at the sequence, "The cat sat," and predict the word "on."
Right. It should have absolutely no idea what comes after sat. It has to guess based on the patterns it learned.
Exactly. But our current matrix multiplication mechanically compares every token to every token all at once.
Right, because of the cross-referencing.
Yeah. During the training phase, the entire sentence is loaded into memory all at once. The multiplication creates an attention score between sat and mat.
But the word mat exists in the future of the sequence.
Exactly. If the model is allowed to look ahead at the rest of the array to predict the next word, it will achieve perfect accuracy during training by simply peeking at the future data and copying the answer.
Wow, so the loss function just drops to 0. You think you built a genius model? But the moment you deploy it to production and ask it to generate text from scratch,
there is no future text loaded in memory for it to look at.
the model immediately collapses.
Completely collapses. It outputs absolute garbage. It fundamentally breaks if you are trying to generate a sequence step by step, but you trained it with future knowledge.
So when is this bidirectional stuff actually useful then?
Looking at the past and future is highly desired if you're analyzing a complete sequence that already exists in its entirety.
Like what?
For example, if you're doing sentiment analysis on a completed restaurant review,
Okay.
you want the word terrible at the beginning of the sentence to be informed by the word service at the end of the sentence. You're just encoding a static piece of data.
Right, because the whole text is already sitting on the server. You aren't generating it, you're just trying to understand it.
Exactly. But for generation, for actually predicting the unknown next step, the timeline has to be strictly enforced.
And our code base doesn't do that.
No, the codebase we've built so far is entirely blind to time. It basically treats the sequence array as a flat space where time travel is natively supported.
That is wild to think about.
It really is.
Well, this has been an incredible late-night session. I mean, we started with nothing but an empty IDE, and we manually built out the core of how a large language model actually thinks.
Step by step.
Yeah, we shaped our input data into matrix X, mapping out our sequence of train cars,
Yeah.
and their embedding manifests to that crucial ND model shape.
Right.
We made those tokens interact by taking the Q matrix and multiplying it by the transpose of the K matrix, ensuring the dimensions canceled out to create that perfect N compatibility grid.
The networking event.
Exactly, the networking of it. And then we debugged the dot product scaling trap, walking through the for loop, to realize that summing up D dimensions causes the variance to explode.
Which requires us to scale down the results so our gradients don't vanish.
Right. Then we upgraded from a single narrow code review to a multi-headed architecture that captures grammar, tone, and context all in parallel by slicing the dimensions.
It's a lot of math, but it's beautiful when it comes together.
It is. And finally, we ran headfirst into the time travel bug, realizing that our perfect math accidentally allows the AI to cheat by looking into future array indices.
It's a journey through the exact same logic puzzles and memory constraints that the engineers who built these foundational architectures actually had to solve.
Yeah.
Moving from theoretical math to functional code requires understanding the mechanical why behind every single tensor reshaping and dot product.
It completely strips away the magic and makes it feel like actual engineering.
It really does.
Which brings us to the end of our session and honestly leaves us with a pretty significant architectural problem to chew on.
A big one.
Yeah. If the elegant code we just built naturally allows every token to see both the past and the future, how exactly do we surgically alter this massive multi-headed matrix multiplication so the future remains completely hidden without breaking the tensor shapes we just perfectly aligned?
That is definitely the puzzle to solve next.
Yes. Thank you for staying up late and diving deep into the code with us. Keep building, and we'll catch you next time.